So let's go over example 4.2. We have two spaceships, one silver and one black, moving at the same, moving from the same point in the positive x direction. Moving in this direction, say positive direction, and with constant acceleration. So this justify why you can use the kinematic equation, because they work with constant accelerations. And in component form, the silver spaceship starts with an initial velocity of positive 2 kilometers per second and acceleration of 0.4 kilometers per second squared. Then the black spaceship starts with a initial velocity of plus 6.00 kilometers per second and has an acceleration of 0.4 kilometers per second. This they are moving in the same direction, but this one is probably starting to slow down, and it has of course started with a higher initial velocity. So what we're asked is need to calculate the time at which the silver spaceship just, this is very important, just overtakes the black spaceship. And B, sketch the graphs of velocity for the two spaceships. So here they've identified the variables. We don't have displacement, and we don't have their final velocities, and we are not given time. This is what we need to calculate, especially when they overtake each other. So for the spacecraft, silver spacecraft, we have this acceleration, and then for the black one we have this acceleration, and the initial for the silver one is this one, and the initial velocity for the black one is this one. So we need to start solving. So let's go to our worksheet. So we are told that they start from the same position. This one started, this is a silver, and this one is the black spaceship. This one, silver spaceship, started with the initial velocity. It is initiated as VIS, and then the initial velocity for the black spaceship, let's call it VIB. So this is an indication that it started with a small velocity. This started with a higher velocity. So we have realized, we have found that these are the values of the variables given in the information. This is the acceleration with the subscript S, as this is for the silver spacecraft, and also we have VIB, the initial velocity for the black one, and the acceleration for the black one as well. So what we can do now, actually this is their relative position. This is their relative position given different initial velocities. So let's continue. So what we are required of is to calculate the time at which this spaceship, the silver one, actually overtakes the black spaceship. So what you can say is that before, even before the silver uh, spaceship overtakes the black spaceship, it needs to reach it first. That being said, that it must be in the same position. It must reach this. It must be at the same position as the black one. Then it can overtake the. It can overtake from there. What I mean that it must have the same displacement as the other. So we need to have. Okay, let's call this one the displacement due to the silver one, and then the displacement due to the black one. So in order to overtake someone, you need to reach him first, and then you need to reach him first, and then from there you can overtake. Reaching someone means you are at the same position as that person, the same thing. This means that their relative position, their positions should be the same. Their positions must be the same. This is all we need. This is the key thing to take here. So actually the time the time at which this happens, where the silver and the black spaceship are at the same position, this is the time of overtaking. This is the time where the silver rocket has a chance to overtake the black spaceship. So now let's identify the variables fully. So if you write down the variables that will be useful for us, is the initial velocity, acceleration, and change in time, the time at which this takes place, and then of course the position at which this happens. So these are the very important variables, and now we can now identify a kinematic equation that best fit this. So this is the one that has, or that satisfy these variables. This displacement is equal to initial velocity times change in time plus half acceleration change in time squared. So this is the equation, and we need to set maybe before we are even set, or we need to remember, we need to set x b equal x s. So we need to set the displacement to be equal. The displacement for the silver rocket and the displacement for the black rocket. So a convenient way to keep track of the displacement, that which is for which, is to give it a different notation for the silver and the black one. So say the first equation, change of xs is equal to, for this is for displacement for the silver rocket, so is equal to vis, which is the change, the initial, this is the initial velocity of the silver, and then times change in time, and then plus half, and now the acceleration due to the silver rocket times change in time squared. And then this is for the silver. Then the black rocket will have this notation: displacement due to the black rocket is equal to initial velocity IB, this initial velocity for the black one, times change in time, or plus half AB times change in time squared. So we have these two displacements. So what it follows now is to equate them. So we need to equate them like this. Displacement due to silver rocket is equal to displacement due to the black rocket. So now we need to equate them. So VAS plus half AS, oh, let's change in time here, change in time squared is equal to VIB times change in time plus half AB change in time squared. So we need to take this side of equation, to that side, so we need to subtract. So if we take all the terms that side, we end up with something like this. So change in time VIS plus half AS change in time squared minus VIB change in time minus, because we've taken it to the other side, half AB change in time squared equal to 0. So now we need to factor out this term to be able to solve the equation. If we do that, if we factor out this term, and then what is inside is VIS plus half AS, and now this is no longer squared because we factored out sorry, it's not clear enough, times acceleration times this term minus VIS VIB minus half AB, this term, then all equal to 0. So this implies that from this equation, this implies that the solution, we have either this equal to 0 or this or VIS plus half AS change in time minus VIB, which is the initial velocity of rocket B, minus half AB change in T equal to 0. So if we group this term and then making it a substitute of the formula, we have, if we group it and make it a substitute of the formula, we get something like this. Change in time is equal to 2 VIS minus VIB all over AB, is the acceleration of the black spaceship minus the acceleration of the silver one. So you can work this, and just to give yourself practice, move from here to here, making this substitute formula and having this form. So now we can substitute the values, because we have these values. We have these values from the information of the problem. So it's simply substitution now. So we have 2 2 multiply brackets of 2 kilometers per second minus 6 kilometers per second all over minus 0 over 0.4 kilometer minus 0.4 kilometer per second, because this is acceleration, and then per second. So what we get is that change in time is equal to 10.0 second. Maybe to note before I conclude is that we were able to work with the kilometers even though it's not a SI unit, because we wanted time, and what important is the SI unit of the time at the end. Even if we could have converted to meters, we could have got the same answer. So what is important is at the end we ended up with a correct unit. So this is the the time it takes for the silver spaceship just to overtake the black spaceship. Since we are done with A, let's go to B. So we expected in B, we need to sketch the graphs for the velocities for the two spaceships. So we need to sketch Vx for the two spaceships. So we have a graph like this, kilometers per second, and then here we have time. So from the information, we sketch using the information. So the initial velocity for, is talking about the silver. Talking about the silver rocket. So the initial velocity was 2 kilometers per second, and we can calculate, and then it took 10 seconds for it to overtake the black one, or the time the time that has elapsed. So we need to find the final we can calculate the final velocity, which is ff, and we use this equation. I think you remember this one. Change in time, where we get, we have 2 initial velocity, which is 2, plus the acceleration, which is 0.4, and times the time, which is 10 seconds. So we get 6. So this is the 6, the final velocity. So it moved from 2 to 6. It increased in velocity. So we have a graph like this. So the area, this is the area under the graph. So this is the area under the graph. So actually you can calculate displacement. Using splitting maybe this area, area 1, area 2. You can calculate, which is not, we are not asked for, but we can calculate displacement. As the area under the graph. So if we say 2 times 10, which gives us, okay, if we say 10 times 2, this area number 1, and we add it to here, the difference here is 4. So remember that equation for area of a triangle is half base times height. So this is the height, which is 4, which is 4, but say half base. The base is 10 seconds. That's the base, and then the height is 4. So we end up, so when you calculate this, you end up with 40 kilometers. We have 40 kilometers. And then you can also verify that the displacement which you calculated from using the area under the graph is 40 by using this equation v I x change in t plus half a change in time. This acceleration for the silver rocket squared. When you substitute here, you'll also get 40. So let's go now to the other. Let's go to the graph for the black rocket. So here we do the same, where we have time interval, then here we have velocity, which is in kilometers per second, and then also here we can calculate the final velocity from the equation, the kinematic equation. By now you know it, and then you can get that. Maybe let me take you step here. Let me take us step by step here. So this means is equal to the initial velocity was 6 kilometers, and then plus the acceleration, remember, was negative, so plus minus 0.4, then times 10 seconds. So this is 6 minus 0.4 times 10, which is 4, which gives us the final velocity as 2. This is the final. Remember that it was initial, and then so it means that at 10 seconds the rocket was at this speed here, and then we have the initial from the data. We have that the initial is 6 kilometers per second, which is 6. So this means the rocket started at higher velocity and decreased. Hence the acceleration was negative. So again, if we can calculate the area under this graph, you can get that the area is also 40. So this is the area, and you can also calculate the area using the kinematic equation, and it will also get the same thing. So that could be an assignment for you to help grasp through the concept. So I think we are done with the. So what you can conclude is that the spaceships have the same displacement during this interval, the 10 second. That's confirmed the assumption we made that when silver and the silver rocket is supposed to just pass the black one, it must have the same displacement, and then we were able to, from that assumption, we were able to calculate the time. Now it's vis-a-vis. We are, in fact, we are confirming that at this time, at that time interval, these two rockets had the same displacement. Assumption was correct.